Hey, good morning, everyone.
Yeah, good morning, Srinath.
All right, so today we'll continue with this probability, and we'll also try to cover some probability distributions, and then we'll jump into hypothesis testing. So, any questions so far, guys?
Yeah, yeah, yeah. Shrikant, I have one question here.
Yeah, go ahead.
So this, just want to you to revise this topic once again. Independent events. How come conditional is equivalent to marginal? I was a little confused here when
Conditional equal to marginal. No, that
independent
okay.
events
So
is
see,
there, no?
okay. So for example, this x and y, these are two independent events. If the x is not conditioned on y, then the probability of x would be equal to probability of x, which is your marginal probability.
Okay, if they are not, if they are
If they are not,
exclusive,
if they are, if they are exclusive. If these two events are dependent on each other, then we have to call it as a conditional probability. In that case, this probability would not be equal to px. That we will see
okay, okay,
when we'll discuss
okay,
the
okay,
use cases. Then we'll understand.
okay, got it, got it.
So usually there are four types of probability. There's marginal, where when we know that these events are independent, then these will, so we need not to look out for any other events. Okay, is there any other event occurred or not? We'll just concentrate on this particular event and we'll find out the probability of that event. Okay, if it is union, then it's all about or. Okay, here these are not dependent. This could be independent or this could be independent. Here we are saying what is the probability either this event would occur or that event would occur. So here we are talking about or, either this or this. So for example, in this case, if these two are the events, then I am talking about this entire shaded region, either this or this. So this is known as union. Okay, so X union Y. And here we use the law of addition, which we have discussed yesterday. So through law of addition, we can go and calculate the uh, union probability. Then joint probability is all about when the two events can occur together. Okay, this is all about and. So if these two events are independent, this x intersection y would be equal to 0. If these two events are like dependent and can be occur together, then we can go and calculate this joint probability again by using a different law, which is known as law of multiplication, which we will discuss in today's class. And the conditional probability, it has altogether a different formula, which we call as a Bayes theorem or Bayes law. Probably you might have heard this somewhere. Okay, and we will use that particular method to find out the conditional probability. So depending on the problem, depending on the use case, you have to identify what kind of probability you have to calculate, and accordingly you have to choose the right method, and then you have to go and calculate those probabilities. So marginal probability is simple. It is all about number of times that particular event has occurred divided by total sample space. Now that will give you the marginal probability. Okay, so this we have discussed yesterday. So any questions on this union law of addition? So I'll just quickly revise. So the union probability is calculated by this law of addition, which says that uh, P x union y is equal to probability of x plus probability of y. These are two marginal probabilities where we are not considering any other event, and we are just considering this particular event and then finding out the probability of it. Then minus of this joint probability. In some cases, if this is not available, uh, explicitly, then you have to go and use the law of multiplication to calculate this joint probability. If wherever it is available, then you can directly substitute that value here and then you can calculate this union probability. So this example we have checked where we have explicitly, they have mentioned that this intersection is probability of this intersection is 56%. So in that case, we directly go and substitute that here and along with the marginal probability of each of these events to calculate my union probability. So that is my law of addition. Okay, and okay, so let's take this example. Okay, and let's solve this problem. Okay, so basically, see, these probabilities and all those things are used in multiple scenarios. And generally, these kind of problems, what we are currently discussing, these are the problems which are related to surveys. When you are going and conducting any kind of a survey, you will get some results out of it. Okay. And based on those results, you go and find out what is the chance that the employees may like this or may not like this. Or, okay, those kind of scenarios you can generate. And based on that, you can calculate the probabilities. And after seeing those probabilities, then you will get some idea that, okay, what people are liking, what the people are not liking, and accordingly, you can take the decisions. For example, in the earlier case, they ran the survey where they have tested that, okay, how to increase the productivity, okay, whether to reduce the noise or increase the storage space or the space of that. The different people have given their different opinion. And based on that, their opinion, they have calculated, they have come up with the different scenarios. And based on that, they have calculated the probability. And based on the probability, they will go and take the decisions, okay, which will work best for them. Now, again, similar problem, a company data reveal that in a particular company, they have done some analysis. They found that there are 155 employees are there who worked in 4 different types of positions. Okay, those positions are these: managerial, professional, technical, and clerical. Okay, these are the 4 types of positions as shown in the matrix. And we also call this matrix as contingency table with the frequency count of each of those category and for subtotals and the totals containing a breakdown. So with this table, you will get a complete picture about how these people have been organized and structured in a particular company. So these are type of position. This is gender. So in managerial, overall there are 11 members. Out of those, 8 are males and 3 are females. Similarly, for professional, this for technical and clerical. So let's suppose you have this data with you. Now, based on this, I will ask certain question which you have to go and calculate. So here, what is the probability that employees either female or belongs to a professional position? So can anybody can calculate? So just now we have seen that law of addition, right? Here I'm talking about what is the probability that any employee is either female or professional. Can somebody quickly go and calculate this? Okay, so let's do it together. So what is the equation? It is probability of F plus probability of P minus probability of F intersection P, right? Now you tell me what is the probability that a particular employee is female? What is the probability? I'm not considering any other event apart from considering whether that person is male or female. So what is
So,
the probability?
so
Yeah,
that is 55 divided by 155.
right. So now you understood this marginal probability. Here we are not considering any other event apart from the gender. Okay. What is the probability of being a professional person?
So that will be 44 divided by 155 again, I believe.
Right. So here we are taking the entire count, just considering only on that event. So that's the reason my denominator is the overall company size. Okay, overall sample space. Now here, you tell me what is the probability of this F intersection P?
So that will be 13 divided by 155.
Okay. Now let's look at the answer. So they have given the ratio. Okay, so you can go and check. So this is how you can calculate this probability of being female or professional. Okay, so that's the
One
how you,
question here.
yeah, go ahead.
Probability of female is 44 by 155 might be, is that correct?
Probability of
Because
female is this. This is the total count of
13, And then
Which
there
one
are
you're
only
talking about?
13 females, right? The second one, probability of female.
Here I'm talking about probability of female only. I am not considering any other event, whether it is managerial, professional, technical, clerical. I'm not considering anything. I'm just considering whether that person is female or not. So what is the probability that if I randomly select any particular employee, that employee is female? So that is overall female is 55 out of 155. So that would be my marginal probability of this particular event, which is uh, employee being a female. Similarly, for probability of professionalism, professional position, total positions are 44. So out of 155, the total position of professional is 44. So 44 by 155 is the probability of picking up any employee which who belongs to this professional position. Now this is my intersection. Intersection is this female and professional both. So which is this 13. So here the 13 is professional and female both. So what is the probability? 13 divided by total number. So that is the probability of picking an employee which would be female as well as professional. Is that clear?
Yes.
Okay. So we shift to another PPT. 1 second. Okay, so this something, okay, I'll give it as an exercise. Okay, you guys just try to solve this particular problem. Again, we have a now bigger data where we have geographical location and the industry type. And based on that, there are some problems. Okay, questions are there. You try to solve, okay, with that data. All right, so now all this. Okay, now let's talk about the law of multiplication. Okay, the law of multiplication says that P x intersection y is equal to, if these two events are not independent, if let's suppose y is dependent on x, then it is denoted as the product of these two probability. So where let's suppose this x is not dependent on y, then for x we will go with a marginal probability, and if y is dependent on x, then we'll go with a conditional probability of y given x. Either this, or if it is a vice versa, then you can also write it as py into px given y. So depending on which event is dependent on which event, you can go with any of these formula. Okay, so for that you have to go and calculate the conditional probability. If these two events are independent and if they can occur together, in those events, those we call as a special case. So in that case, conditional probability will be equal to marginal probability, as we have just discussed. So in that case, the P in x intersection y would be the dot product of these marginal probability. So because the marginal probability is considered when these two events are completely independent and they are mutually exclusive. Okay, in that case, one event is not dependent on another event, and then the dot product of these marginal probability would be equal to the joint probability. If any of the events are dependent on other event, then you can go with this particular formula where you have to consider uh, one probability as a conditional probability and another probability as a marginal probability. Okay, so that is known as law of multiplication. Now how we can calculate the conditional probability? Now this particular equation is called as Bayes theorem. Bayes is a person's name, who has came up with this particular equation. So now, see, the way it has been derived is P x intersection y is, just now we have seen, it's x given y. into Ty. Okay. Or else, okay, so you can just just alter this equation. You can put it like this. If you want to calculate the probability of x given y, it is the way we say that we call this particular probability is we say that probability of x given y is equal to joint probability of these two events divided by the marginal probability of y. Okay. So I just brought this particular probability down here. Okay. So you can put it in this way. And we also know that if the dependency, if the both the events are dependent on each other, x and y, if y is dependent on x and x is also dependent on y, then we can also put it in this way. Probability of y given x into probability of x. This particular part, numerator, is nothing but px given y. Okay, we have seen it here. Okay, we can put it, okay, either like this or like this. Okay, divided by py. That would be equal to px given y. So now this is known as Bayes theorem, where both the events are, related to each other. Okay, are impacting each other. So in that case, we go with this Bayes theorem, which is known as conditional probability. So the conditional probability of x given y is the joint probability of x and y divided by the marginal probability of y. So this is the equation. If these two events are, of course, are not independent, that's the reason we are going with this conditional probability. So instead of writing like this, we can write the equation like this. Now this will become my entire Bayes theorem. So this Bayes theorem is very important, guys, when we deal with certain machine learning algorithm, which are mostly probabilistic based algorithm. There we use this Bayes theorem, to understand which all events are impacting your target variable. For example, if you want to find out what is the probability whether that customer will buy my product, okay, so now you have to go and look out the historical data and see whether customer's gender is impacting the purchase or not, whether those two events are related to each other or not, whether the customer age is impacting, will influence the purchase or not, whether the customer's region will drive the sales or not. So like that, it will look out for multiple events and see that how much each of those events are contributing on the final purchase. And that's how that algorithm will learn based on the probability. And once the model is trained, now you can just pass the characteristics of those customers and it will immediately calculate the probability and show you that whether the chance of purchase is 90% or 80% or 30%. And based on that, business can take a decision. Okay. All right. So now let's take this example and quickly we will see that how this conditional probability works. For example, from the used cars lot, 70% have air conditioning. Okay. And 40% of the cars have CD players. Okay. And the 20% of the cars have both. Okay. So this is the kind of information what we have about all these used cars. Now we have to go and find out what is the probability that car has a CD player given that it has an AC. Here, both the events, okay, I'm considering AC as well as CD player, both. So we want to find out what is the probability that any car which is having an air condition in it is also having a CD player. So here the sequence matters. Okay. And this sequence is important because I'll also talk about one use case where this sequencing will play a very important role. Okay. If you consider the probability of AC given the car is having a CD player, that would not be equal to this CD given AC. This would be different. So now you need to understand what condition you want to apply. So for example, what is the probability that today there would be a traffic jam given it is raining. Rather than if you go and say that what is the probability that it will rain given there is a traffic jam. Okay, so the sequence matters. So here we want to find out what is the probability that a car will have a CD player given it has a air conditioning in it. Okay. Now, whatever information is given to us, I'll create this probability matrix or a contingency matrix. Okay, where I'll mention. Okay, so here they have mentioned that 20% of the cars have both. So CD as well as AC, it's having 20%. Okay. Only CD is having 40%. Only AC, it is having 70%. So whatever I've circled, those information is given to us. If this information is given to us, then we can go and calculate this particular information, right? So from 0.7, I will subtract this 0.2. I can able to find out this 0.5. Okay. 0.2 is given, so this I can calculate. Okay, and the total, yeah, this I know, the total probability has to be 1. So with this, I can calculate this. If this is there, I can calculate this, and then I can calculate this. So like this, I can create the contingency matrix. With the limited information, I can able to fill all these values inside this probability matrix. Now I have to go and calculate this probability. So what is this probability? P CD given AC is equal to probability of CD intersection AC divided by probability of AC. Now with this probability matrix, you can easily identify these values and you can substitute that into this formula to find out this conditional probability. So probability of CD and AC. So CD and AC is 0.2. Okay, that is my intersection, 0.2. Probability of AC, which is this 0.7. So with this, I can able to find out this. So let's suppose I want to find out probability of AC given CD. Now tell me, guys, what will be the answer? This will be the same intersection. It would be 0.2. The marginal probability will change. Here we have to consider the probability of CD, right? So probability of CD is what? 0.4. Okay, so this is the probability of AC given CD. Now you clearly see that, okay, these are not same. Okay, so the values are different. All right, so you can use this decision tree as well. Okay, so I'll not confuse you. If that is clear, then let's skip this. Okay. Okay, so these are all examples. Okay, so that's about conditional probability. Now we will quickly refer to the distributions. Now we have seen that, okay, with the probabilities, we can able to calculate certain kind of probabilities specific to particular scenarios. Now things have become easy, will even become further easy, if we understand different probability distribution also. So I will talk about probability distribution, and in the statistics we'll refer to this probability distribution because it will make our job easy in terms of calculating the probabilities. Okay. So now let's first understand what are these probability distributions and then we get into each of those distributions. So basically, just understand, okay, as I mentioned, in statistics, it's all about sampling, right? So in sampling, we pick up randomly certain values. Okay, it could be discrete or it could be continuous. Discrete means where you are just taking where the values are could be the countable numbers or it could be certain categories. Those are known as discrete. While continuous, the values could be any decimal, could be values with any decimal places. Okay, those will be continuous. Now, when I'm randomly picking the observations, okay, or the values from a particular population, now that particular uh, selection of the values may follow certain kind of distribution, okay, certain probabilities. So as we have seen that in the normal distribution, if we are taking out the sample from the normal distribution for picking a particular value, okay, we can easily go and calculate the probability by referring to that normal distribution. You need not to worry about the sample space or all those things. So there is a formula defined, and by using that particular formula, we can easily identify the probabilities. And things have become very easy by by using those tables, Z tables and T tables, because they have defined the distributions, and underneath whatever formula is there, they have used that formula on different parameters and they have constructed that table. So rather than going and calculating the probabilities on your own, you can directly refer to those tables, and then you can calculate the probabilities. So basically, the distribution is nothing but it is describes you the shape of a particular data. Okay, and that data comprises of, it can be a continuous variable, it could be a discrete variable, and based on those batch of numbers, you can define its shape. Okay, and that is nothing but a distribution. Okay, and this distribution, the characteristics of this distribution can change based on certain parameters. Okay, so for example, the standard normal distribution, it has a certain characteristics where the mean is equal to 0 and the standard deviation is equal to 1. Now that they have defined it as a Z distribution. Okay, and another different kind of normal distribution, it could be any number other than 0. Okay, so and the sigma may also change. If we have those kind of scenarios, instead of going and referring to the Z table, then we can go and use the formula. Okay, and using that formula, we can calculate the probabilities. So now, how how many number of such distributions are there? Which distribution to use where? Okay, that comes by knowledge and that comes by experience. Okay, generally wherever we are dealing with continuous data, we normally go with a normal distribution. And whenever we are going with a normal distribution, if we have to assume that the data is kind of distributed as standard normal distribution, then we can go ahead and refer to the Z distribution. If not, then we go and refer to the formula. So which we will discuss. Okay. So distribution in statistics, these are, you can consider it as a reference. Okay, you can refer to those distribution to calculate the probabilities easily rather than going and calculating by hand and understanding whether it is a what kind of probability you have to use to calculate those probabilities. So why distribution? As I mentioned, these are, in statistical procedures we make a lot of assumptions. And see, I'll tell you the importance of this distribution in several ways. One is like for inferential statistics, when we have to infer something about the population, and if we have some understanding about the population distribution, then we go and directly refer to this distribution and apply that on the sample to make certain conclusion about the entire population. Okay, that we have seen, right? When we were discussing about that confidence interval and all those things, there we have seen how where we have considered the Z distribution, somewhere we have considered the T distribution. For different scenarios, we have considered different distributions. Okay, that those are like theoretical concepts, and it has been stated very clearly that okay, in these kind of scenarios, you have to refer to these distributions. That is one. Second is if you do not have the data available. So, for example, you do not have the population data also along with you, and now you have to go and do some kind of analysis. But in that case, if you have some understanding about the distribution, that this particular population uh, is basically will have the normal distribution, okay, and where the mean is equal to 5 and the variance is equal to 2, let's suppose. Like if you have some indication about these parameters and about the distribution, then you can use these distribution to generate the data also. And now that whole process is called as Monte Carlo distribution, Monte Carlo simulations. So through these simulations, okay, we can generate the data. Now, your question would be where exactly we use this. So, for example, in banking, we do not have the data related to fraud because we will have very limited data related to fraud. Now, if you have to go and develop some kind of a fraud detection model, we need to have a good representation of fraud in my data. If I have only one or two such data points related to fraud, my model may not able to learn anything out of that data, and I cannot able to build any fraud detection model. So in that case, I will, if I have an understanding that this particular data, fraud data, follows this kind of distribution, then based on the probability, I can generate those kind of scenarios, and that is known as simulation. So this distribution can help us in terms of simulating the data and generating those kind of scenarios in the data if I do not have that data available with me. So that kind of simulations can be only possible if you have any understanding, some understanding about the distributions. Okay. Now we talked about distribution. Okay, and this distribution in statistics we call as a distribution of a random variable denoted as a capital X. Okay, and this random variable can be discrete, can be continuous variables. It could be something like this. Okay, for example, now you are tossing a coin. Okay, and the tossing a coin would be the your random variable, and what values it may take, it may take either head or tails. So these are the only two values this particular random variable will take. Now I have to generate multiple trials. For multiple trials, I have to generate the values. Okay, so one way is like you go and perform those trials. Okay, that many number of times. So for example, 100 data points I need. So you have to go and toss the coin 100 times, and you have to go and capture all the values, after the trial, and you have to generate the data like that. Or else, if you have some understanding about the distribution of this random variable, then you need not to go and perform those trials, those experiments through the distribution. If I know that the probability of head is only 25%, then in 100 data points which I'm generating, this particular the probability distribution will tell, like, how many times this heads may come. Okay, it's all about random. Okay, it will generate the values based on the probability of heads. So like that, these distributions are helpful in terms of predicting or calculating the probabilities, as well as, in generating the data. So these are the two major usage of these distribution, in calculating the probabilities and inferring about the population, and the second in terms of generating the data wherever we do not have the data. Okay. Let's give you an example. So, for example, now let's suppose you are tossing 2 coins. Okay. When you are tossing 2 coins, there could be three scenarios which you may come across. One is like you are not getting any heads. Okay, you are getting both the tails in both the coins. That is like 0 heads. Getting one head, or getting 2 heads. Okay. Let's suppose you know the probability of these kind of scenarios. And these are all mutually exclusive events. Okay. When you are getting 0 heads, you cannot get one head. Okay. Along with that. So these are all mutually exclusive, and the total sum of the probability is equal to 1. So collectively exhaustive. Okay. So if you draw the probability, the distribution of these scenarios, it may look like this. Okay. So this is the probability density. We called as a probability density function, PDF. It is on the Y column, and this is on the X column. So probability of 0 is 0.25. Probability of 1 is 0.5. Probability of 2 is 0.25. So this distribution looks like this. And sum of all these probabilities will be equal to 1. Now, if you know the probability like this, now you can do multiple trials on it. So you know that number of getting 1 heads has a 50% chance. Number of getting 0 heads is 25% chance, and number of 2 heads, getting 2 heads has 25% chance. So if you know the chance, okay, you can able to generate the values. So if this is the scenario, then probably whatever number of data points you will generate, there is a high chance that you will get more of ones, okay, and less of zeros and twos. Okay, So in that particular data, in any kind of scenario, if the probability of this is high, like 0.5, and this is 0.25, then in those scenarios, the chance of getting 2 would be higher. Okay. And if anybody has gone to any casinos and all, okay, there you will see this kind of information. Okay. They'll say that, okay, by now, 0 head, the chance is only 25%, getting 1 head is 50%, getting 2 heads is 25%. They will show it in the screen, on the screen. And based on that, you have to take a call. So again, it is not 100%, right? It's just the probability. So you will go and bet it on a higher probability scenarios. Okay. So there would be high chance that you may win that. Okay. So by looking at that statistics, people come and, they bet on the game. Shall we cover this? Okay, this will cover later. Okay. So for example, now you have some kind of an idea about the crisis, daily crisis. So in any region, getting 0 crisis, the probability is 37%. And people kind of, they capture this kind of data with them. So number of crises, and the probability of occurring of that many number of crises, they will kind of collect that. So that is this. Okay, this is known as distribution. Okay, so here we have the probability on the y-axis and the number of crises on the x-axis. So this is the distribution, and by now this is the maximum number of crises which has occurred. Okay, so total the probability would be equal to 1. If you add this, it will be equal to 1. So those are the only scenarios which have occurred so far. So they have come up with the probability. Now, if somebody asks them, okay, what is the chance that, okay, today there would be a 0 crisis, it would be a 37% chance. So if I have to generate the data, okay, for something, for my analysis, for my model building or something like that, I will refer to this distribution and I will go and generate those values. So I may get in my data more zeros because the probability is high for this particular value. So here the probabilities are given. So that's the reason I can go ahead and generate the data. Sometimes the probability would not be given. In that case, I have to assume a distribution is following such kind of pattern, and it follows this kind of parameters. And based on that, there would be a formula which I can use, to calculate this probability density function. Okay, so for a different kind of distribution, we have a different formula for this PDF. Okay, based on that, I can go and calculate the probabilities. So why I'm talking about all those things, guys? Okay, now these are like very important distributions, and when we have to infer about any particular scenario, we can quickly refer to this distribution, and then we can draw some insights of that particular scenario, and we can make a decision. So once we discuss about the use case, these things will be further clarified. Now I'll quickly jump to the distributions so that it would be easier for you to relate. Da, 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 da. Okay. I'm just talking about some special distributions, but there are several distributions, okay, which are there in statistics. If you have a understanding about a particular scenario, then you can choose those kind of distributions. So recently we have solved one problem related to warranty. Okay, here the customer wanted to estimate the warranty cost, extended warranty cost of their products. So generally, the claim of any particular product, generally in statistics, it has been defined that it will follow us some kind of a pattern which will be closer to a one particular distribution known as Weibull distribution. So we have considered that distribution to identify how many failures may occur for a particular product in a particular time period. So based on that distribution, we have calculated the probability of like 0 failure or 5 failures or 6 failures. And based on that, we calculated the cost, the average cost. And that we have estimated as a warranty cost, warranty price for that particular product. So like that, if you understand the scenario and if you can relate it to a particular distribution, and there are certain techniques also. If you have a data, historical data, you can identify also what distribution that particular data is following. Okay. And based on that, you can further generate the data. So that is also possible. But for now, let's talk about this some special distribution. If you have a discrete data which is like you can count and which are not continuous, which is not in a decimals. Okay. Uh, for that, we have these special distributions known as binomial, Poisson, hypergeometric. Okay. And for continuous data, which is numerical data, which are in decimals, for that, we have these three distribution: uniform, exponential, and normal. And we will understand in which kind of scenarios we use these kind of distributions. And these distributions will quickly help us, to calculate the probability. And why are we covering in data science? Because see, if you know about the probability, you can able to understand whether that particular event would occur or not. So basically, we are doing nothing but the predictions here. So probability is nothing but the prediction. So based on these distributions, we can able to find out the probability of a particular event to occur. And based on that, we can able to understand whether that event would occur or not, and accordingly we can go and take the decisions. Now let's take the example. Okay. Now in my store, okay, uh, customers come and they buy the product. Okay. Now I want to understand what would be the purchase decision of the next three customers who will enter my store. On the basis of the past experience, the store manager estimates that probability that any one customer will make a purchase is 30%. So anybody, whoever is walking to my store, I know that, okay, there is only 30% chance that that person will, will buy my product, will make any purchase. Now I want to know what is the probability that two of the next three customers who are walking into my store will make the purchase. Are you getting this problem? Now, these you can relate it in the e-commerce also. Okay, let's suppose there's a lot of traffic which is coming on my website, and I want to understand, okay, the next 3 or 4 customers, whoever comes onto my website, out of those 4, 3 will make the purchase. So those kind of probabilities I want to consider. So if the probability is low, that means something wrong in my website. People are coming, but they are not making purchase. They are not purchasing anything. So that's something I want to fix it. If let's suppose out of 10, let's suppose 6 people are purchasing, that means 60% is my hit, okay, ratio in terms of customers getting converted to the sales. So that's something, okay, I want to calculate. For this, how the very traditional method is, you go and build those uh, decision trees, okay, which we have just seen, right? Those kind of, so I have first person entered into my store, either he will make a purchase or he will not make a purchase. Then second customer, he will make a purchase or he will not make a purchase. Here also the first person not making a purchase and second person making a purchase or not making a purchase. Again, third customer. So those many scenarios will be there. Okay. So all the 3 people making the purchase, it's PPP. This could be one scenario. It could be a scenario where all the 3 people are not making a purchase. And there could be a scenario, any of the 2 people, they are making a purchase. Okay, so that would be my sample space. You have to create this kind of a decision tree. And out of the decision tree, you have to make sure you have to go and find out the 2 people making the purchase, those scenarios, and then you have to divide with the total sample space to calculate the probability. So it is a kind of a long method, to calculate the probabilities. Now you will see that through this binomial distribution, just with a single formula, we'll just plug in the information and we can calculate the probability. Okay, very quickly. So yeah, so this is that decision tree diagram. Okay, the first customer, success or failure. So S means purchase, F means no purchase. So like that, I will create this kind of a tree. If I'm interested only 2 people making a purchase, then this is one scenario, this is another scenario, this is another scenario. What are the total number of options or the outcome 1, 2, 3, 4, 5, 6, 7, 8. So 3 by 8 is the chance of that person, 3 people making a purchase. But here what I have, but this is may not be accurate because here I have taken 0.5 and 0.5. There is a 50% chance that person will make a purchase and it will not make a purchase. If it is like fair kind of a scenario, there only this particular method would work. But here I am saying that any customer making a purchase is only 30%. So failure percentage is 70%. In that case, this would not work. This particular method would not work. In that case, I have to refer to some other method. Okay, what is this method? This is this method. So for example, I've taken all the scenarios of two customers making a purchase. Okay, the first person making a purchase, second person making a purchase, and the third person not making a purchase, and similarly other two options. So here I will take the, so now this is a joint probability. It's a probability of S intersection S intersection F. And with the multiplication rule, as these are all independent, I'm not saying that, okay, the second person is getting influenced by the first person. If the first person is making a purchase, then only the second person is making a purchase. I'm not considering that. So these are all independent events. So here, this particular thing, if I want to calculate, I can just write it by using the multiplication rule. I can write it like this. Yes or no? Are you following till now? Guys?
Yes, sir.
Let me know, guys, if you are having any confusion. So I'll try to explain it again. Is this part clear? See, now just simply put it in this way. Okay. I want to calculate what is the chance that out of 3 people coming to my store, 2 people will purchase my product. And I'm giving this one disclaimer that any one person buying my product, there is only 30% chance. Okay. Here, if I take this particular kind of a decision tree and count only these options and divide it by total sample space, that may not work because I'm taking every event as a equal probability. Like, okay, so here in this case, it is 0.5 and this is 0.5. But in this particular problem, it is clearly stated that any one customer buying the product is only 30%. Okay, probability. And not buying a product is 70%. So what I will do is I will come up with all those outcomes where 2 people have made the purchase. So first one making a purchase, second one making a purchase, and third one not making a purchase. Now this collectively I have to calculate the probability. So for that, I will go with this law of multiplication, which calculates the joint probability. So now this is the joint probability. I want to find out what is the probability that first person making a purchase and second person making a purchase and third person not making a purchase. I'm talking about and. Okay, all these events have to occur together. So in that case, I will go and use this law of multiplication because all these events are independent. So those are not conditioned to previous events. So now this would be my joint probability. So now here the statement is they have clearly stated that the probability of success is equal to 30%. So I'll make it as probability of success as P into P and probability of failure as 1 minus P. Is this clear? Probability of failure is what? 1 minus 30%, 70%, right? Probability of success is 30%. So I'm just denoted it as P. So it is P square 1 minus P. In this particular kind of scenario, it is probability of success into probability of failure into probability of success. Now this would be also P into 1 minus P into P, which is also P square into 1 minus P. This would be also P square into 1 minus P. So 2 times success, the probability of the success square and into probability of failure. Okay. So now this is the formula. So like that, this binomial distribution has come up with a equation like this. Okay. So this is known as probability density function for this binomial distribution. Okay. Now we will put it in the formula. Now this is known as combination. Okay. So we have NCX. Okay. Where NCX is factorial of n divided by factorial of x into n minus x. Yesterday we have seen, right? Where we are talking about without replacement. So this will give me the number of combinations of success. Okay. That into probability of, that many number of scenarios it will tell. Okay. So here in this case, there are three scenarios. Okay. So if you say 3 into p square 1 minus p will give me the total probability of these three outcomes. That would be my answer to that particular problem. When I'm saying that what is the probability that out of three, two will purchase. Okay, that is given by this particular formula. Now, this how it is coming. This is the number of combination, number of scenarios that is coming by this particular combination formula known as NCX, where X is number of success and N is total number of trials. So here P means the probability of success raised to the power number of successes into Q. Q is probability of failure raised to the power n minus x. N is means number of trials minus x. Okay. So this is how you can use this direct formula and you can solve any kind of problem. Okay, any scale of problem. For example, if I say out of 100 trials, what is the probability that I may get 3 success? So here n is equal to 100, x is equal to 3. And if I say the probability of success is 20%, if I know these three parameters, I will substitute that into this particular formula and I can able to find out what is the probability of getting 3 success out of 100 tiles. Okay, that I can derive through this particular formula. So now see with this binomial distribution, if I know, how this, in this particular scenario, what distribution would fit into, then I will use this particular formula and I can able to calculate the probability. So that is the use of this distribution. Now for that, people have also came up with this kind of binomial tables that just like Z table. You can refer to this particular table also where n is given, x is given, and p is given. These are the three parameters which you need to know if you have to go ahead with this binomial distribution. So if you have these three information with you, you can able to calculate the probability. Okay. Now let me give you a scenario. Okay, so here my problem was what is the probability that there is a what is the probability of two people or two customers buying my product, okay, making a purchase. Now tell me what is the probability of having at most two people buying or making a purchase. How you will calculate at most two? What do you mean by at most two?
So that will be 1 minus 0.027.
Yes, but what do you mean by at most two? That answer is correct, but what do you mean
So
by
it
at
will be
most?
0, 1, or 2. That's it. So that
Yeah.
includes
So at
all
most two
probability.
means till 2, okay, from 0 till 2. What is the probability? So now what you can do is you just go and calculate the probability of 0 success, 1 success, 2 success, and 3 success, okay? Or else you just calculate the probability of 3 successes and just subtract it from 1, okay? That will give me the probability of at most 2. If I say what is the probability of at least 2?
So it will be 2 and
0,
3.
At least
1,
two. At
1
least.
minus 2 and 3.
At least two, I'm saying.
Yeah,
At
that
least
means probability
means
of 2 and
2
3.
and 3, right? At least means 2 and 3. Minimum that has to be 2. 2 and 3. So now you have to add these two probability that it will give you the probability of at least 2. Okay. So if you know this kind of distribution, okay, if you know what could be the maximum number of successes, so see, the maximum successes would be equal to number of trials. So if you are going with 100 trials, maximum success, how much you will get? You will get 100 success. There could be a chance that in all the trials you will get the success. If all the customers, whoever is coming onto your website, they are buying your product. Okay, that would be the number of success. So here X can be range from 0 till number of trials. Now you find out the probability of each of the values. Now this X is known as random variable. Now this random variable can take any value between 0 till n. And now this would be your X variable, random variable, and here the values would be from 0 to n. In this case, the number of trials was 3, right? The number of, so I was interested in every 3 customers, whoever is coming to my store, what is the probability that 2 customers will buy my product. So here the number of trials is equal to 3. So the range would be from 0 to 3. Now what I have done is through using this binomial distribution for every number of success, I calculated the probability. For 0 success, I used that particular formula and calculated the probability. For 1, I calculated the probability, 2 and 3. Okay. Now I came up with that probability of each value, okay, this random variable may take. Now, if I have this kind of a distribution, now I can calculate any kind of probability. I can calculate the probability of getting exactly 0 or exactly 1 or at least 1 or at least 2, at least 3, whatever. Okay, so if I know this distribution, it would be easier for me to calculate or probability of any kind of scenarios. Now, based on those scenarios, I can able to make the decisions. Okay, now if you say that, okay, now it shows that, okay, the probability of exactly one person making a purchase is around 45%. What is the probability that at least one person should make a purchase is this plus this plus 3. So what it would be 0.441, 0.18, 0.27. Let's suppose if it is coming more than 50% or more than 60%, then I'm good. At least out of 3, at least one is making a purchase. So that's something, okay, if I can able to calculate, I can look at various scenarios and accordingly I can make a decision. Now see here, this random variable X can take what values? Can take 0, 1, 2, and 3. Okay. Can it take in any other number apart from these 4 values, guys?
No.
No, right? So can I call this particular variable as categorical variable? Yes,
Yes.
because this particular variable can take only these 4 values. It cannot take 0.5, it cannot take 1.5. So that's the reason I can call it as a discrete, and discrete that too categorical, because it can take only these 4 categories. Okay, nothing apart from this. So in your data, if you have one variable like this, which has only 4 categories, then you can use this binomial distribution to generate data for that particular variable. If you know these 3 parameters, okay, which is n, where is that? Yeah, n, x, and p. If you know these 3 parameters, you can go and generate the values through this particular formula, through this distribution. Okay. All right. So now let's get into another distribution. Now this is known as Poisson distribution. Now where we use this. Okay. So for example, if I want to find out what could be the number of occurrence, in a particular interval. Okay. If I want to find out For example, number of defects in 1 hour, okay, or number of people entering into my store per day, per hour, okay. If I want to calculate, if I want to measure the rate of any event to occur, then I will go with this Poisson distribution, okay. And these are described as the rare events, okay. For example, uh, arrivals at the queuing systems, for example, at the airports, number of people coming into the terminal, in an hour, okay. Number of airplanes landing on my runway, okay, in an hour, or number of automobiles coming in to my parking area, okay, in an hour, or in a day, in 2 hours, or in 3 hours. Number of baggages which are coming for claim, okay, in particular time period. So if I know the occurrence of these events in particular rate, okay, definitely the business will use that particular information to manage the infrastructure and the resources, right? Why we are seeing the airports are becoming bigger and bigger? Because they're seeing that, okay, there is too much of queuing happening, lot of crowd is coming in terms of even people, the baggage, the automobiles. Okay, so that's the reason they are expanding the airports. Okay, they will manage that many resources. So again, they cannot just go just like that. Okay, so in one particular day, if there is too much of crowd, they will not decide, to expand the airport. They want to see what is the chance that this kind of scenario would occur. If, for example, if 100 people entering into the airport at this in an hour, if the probability is high, let's suppose 60% or 70%, then they will take a decision because there is a high chance that, okay, this kind of scenario may occur. So for that, what kind of distribution or how we should calculate the probability is that we can refer to this Poisson distribution. We can calculate the probabilities. Okay. Similarly for the banks, okay, how many loan applications are coming in a day? Okay, so they have to maintain the SLA, right? So they cannot take days together, to process one single application, right? If 100 applications are coming, then they need more manpower. They need more, automation or resources, to screen those applications. Similarly, in computer file servers, how many read and write operations are happening? Okay, so for that, how many servers are required? All that kind of planning can be done, if you can calculate the probability of those occurrence. So, for example, what could be those occurrence? The number of defects per 1,000 feet of copper wire, or number of blemishes per square feet of the painted surface, or the number of errors per type purchase, or the number of people entering into a bank or entering into the airport. So all those kind of scenarios, if we have to analyze, then we can refer to this Poisson distribution. Now, this is even much more relatively simpler than binomial distribution. Here to calculate the probability, okay, we go with this particular equation, which is lambda raised to power uh, x. X can take any value depending on the scenario, and this is the rate of occurrence. Okay. So we just need three parameters. One is the lambda, second is the x. Only two. E is known to us. It is the base of the natural logarithm, which is 2.71. It is a static number. So we just substitute those values into this and we can calculate the probabilities. Let's take an example. Okay, so for example, I know that roughly around 3.2 customers come to my store in 4 minutes. Okay. Now, if I know this rate of people coming to my store in a particular interval of time, now I want to calculate what is the probability that 10 customers will enter into my store in every 8 minutes. And these kind of scenarios or this kind of analysis I want to do. If I have this is a large scale rate, okay, long run average, okay. So generally people whoever in the domain, they may get some idea about, the occurrence of these events. They may say that around 3 to 4 customers generally come to my store in every 2 minutes. Okay. Now I want to quantify it. Now I want to find out what is the probability that, okay, tomorrow I may get 10 customers or 20 customers. And based on that, I will make a decision. So first of all, I will adjust this X based on this rate. Now here, the rate is per 4 minutes and I want to measure per 8 minutes. So what I will do is I'll adjust this lambda. So what I will do is I'll multiply that. So this rate has to be standard. Okay. So I'll multiply by 2. So it will become 6.4 customers per 8 minutes. That is a standard rate, what people are telling me, okay, who are in that particular domain. Now I want to I want to calculate what is the chance that I will get 10 customers, okay, per 8 minutes. Now I'll take this particular equation. So here the lambda is 6.4, which is this. X is 10. This is 10 customers for which I want to calculate the probability. Again, this X is a random variable, okay, which can take any value. So what is the chance that this particular random variable may take a value as 10? Okay. So E we know, this is lambda, again 6.4 divided by factorial of 10, which is X. So that will give me the probability of X equal to 10, exactly 10. Okay. So it is saying 5%. Now what exactly, this is for exactly 10. Now what I will do is I will calculate for 11, I will calculate for 12, and then I will see that, okay, from what is the probability that I may get a customers from around 10 to 15. So that together, I will calculate. And based on that, if it is coming out to be less than 20% or 15%, then I will take a decision in some way. If it is more than 30% or 40%, then I will take a decision in another way. Okay, based on that, I will take some actions. Okay. Similarly, here it's lambda is 3.2 customers per 4 minutes, and I want to calculate for 6 customers per 8 minutes. Again, I will adjust for 6 customers. It is saying that it is 16% chance. There's a 16% probability that, okay, we may get 6 customers in 8 minutes. But what is the probability of getting 10 customers? It is quite low, 5. So accordingly, I can plan. So here the chance of getting 10 customers is very low. So I'll give you another scenario. It is widely used in call centers. So in the call centers, we randomly get a call. Nobody has any idea, like, when we will get a call, right? Okay, so let's suppose we know that, okay, we will get around 4 calls per 4 minutes. Okay, now we have to plan the number of resources, right, in a particular shift. So I will go and find out the probability that what is the probability that I may get 10 calls, okay, in 4 minutes or in 8 minutes. If the probability is very low, I'm fine. Okay, so there is only 5% chance. Even if it comes, even if I'm not able to address all the 10 calls, I'm okay, because there is a very rare chance that I will get. But here, for 6 calls, it is pretty high, 16%. Can I take a risk of missing those calls? Probably not. So I will plan for 6 calls in 4 minutes. So that many resources, I'll make it available. For 10 calls, it's okay. I can fine, because there is only 5% chance. So like that, okay, you can plan your things by calculating the probability of an occurrence in a particular rate of interval. Okay, for that we use a Poisson distribution. And again, we have a table available. Okay, so for different X and lambda values, okay, somewhere it is also denoted as mu, because in Poisson distribution, where it is gone. Here the mean value is for this kind of distribution, mean value is also lambda, variance is also lambda, and standard deviation is square root of variance, is lambda. So lambda, which is the rate of occurrence of an event, is a very important parameter for Poisson distribution. I'll take a pause. Let me know if you have any questions. Is this clear? Now you're seeing that, okay, different scenario, what kind of distributions we are using. So if you want to become a good statistician, then you have to understand all the various distributions, and you need to understand where to fit those distributions, where to refer those distributions to solve your problem. Yeah, you can adjust anything, sort of, you can adjust. If my interest is to calculate at 8 minutes only, then I will go and adjust lambda. If I'm fine to calculate X, at 4 minutes, then I will go and convert this into 4 minutes. I'll divide by 2. Okay. So it depends, okay, which one you want to adjust. But these two has to be on a same interval scale. Clear?
Yes.
Is there like sort of examples wherein if this kind of scenario occurs, we can use this type of distribution?
Yeah. So see, earlier it was more about uh, in what number of successes I may get in number of trials. So if you are if you are facing that kind of scenario, then you go with a binomial distribution. Here for Poisson distribution, if you are measuring the probability of the number of occurrence in a particular rate of interval, there you have to go with a Poisson distribution. So you have to note it down. Okay. So so depending on the scenario, you have to choose those kind of distribution to calculate the probability. So in the earlier case, in the binomial distribution, there is no rate of occurrence, right? Where there we are not talking about per 1 day or per 8 minutes or per 1,000 feet. So we are not talking in those terms, right? If we are talking about in the form of rates, then by default you have to go with the Poisson distribution. There in the binomial distribution is more about the number of successes I may get. So for example, if I'm testing clinical trials, okay, if I'm testing a particular drug, let's suppose if I'm running 1,000 trials, and what is the probability that I may get 600 successes, okay, in out of 1,000 trials, there I will go with a binomial distribution. If I want to find out what is the probability of getting at least 100 successes or at most 600 successes, okay, there I will go with a binomial distribution. Are you getting?
Got it. Yes.
So here also, what is the probability that I may get at most 10 customers per 8 minutes? There I will go with, here I'm talking about rate. Here I have to go with the Poisson distribution. For Poisson distribution, what I have to do, I have to go and find out the as when I'm saying at most, I have to find out 0 till 10. I have to go and calculate for all those scenarios the probabilities, and I have to sum it up. That will give me the probability of getting at most 10 customers per 8 minutes. Okay, so like that you have to select this distribution to calculate the probabilities. Now comes the hypergeometric distribution. Now this is so here we are considering a finite population without replacement. So so here I'll explain it by a example. Okay. So for example, in a particular company, okay, so different computers are checked, and from 10 in the department, 4 of the 10 computers have been found that they have illegal software loaded. Now here the management want to calculate the probability that if I randomly select 3 computers, what is the probability that 2 of the computers may have a illegal software loaded? So see, it is little bit similar to the binomial distribution, but it is slightly different than that. So here, what is the chance that a computer is having a illegal software loaded is 4 by 10, okay, which is 0.4, 40% chance. So here I know the probability. So here the success means finding out finding whether that computer is having a illegal software is nothing but the probability of success. Okay, here it is 40% chance. Okay, now here I'm saying what is the probability that 2 of the 3 selected computers. So there we were saying what is the probability that 2 out of my 3 customers coming into my store will make a purchase. Here I'm saying what is the probability that 2 of the 3 selected computers have a illegal software loaded. Okay, so now here there is a difference. Here those events, here the events are kind of related. Okay, they are not independent. They are the customers buying or not buying. They are independent. Okay, but here it is dependent because see, if I selected out of three, if I selected one as illegal computer, okay, then out of two who are remaining, the probability may change because I'm saying out of the entire number of computers which are available in the company, there are only 40% of the computers are having a illegal software. So there is a count of illegal software or illegal computers. Okay, if I'm selecting three randomly, and out of three, first one is found as to be an illegal software loaded computer, then the probability of the second computer as illegal would depend on this first selection. Yes or no? If it is not, then there would be high probability that second would be again illegal. Okay, if the first has already selected as a illegal, then the probability of second again being an illegal would be relatively lower. Okay, so here these are known as this kind of sampling is known as sampling without replacement because see for example these are the number of computers. Okay, let's suppose in my company. So I picked one. Okay, now this is coming as to be as illegal. Now there are only limited illegal computers in my company. Okay, so again, a second computer picking as an illegal is dependent on this first one or not? Yes? Okay, so let me put it in this way. Okay. So let's suppose these three are square items and these two are circular items in this box. And you don't know anything. I covered it with a black cover, okay, and you cannot see through this particular box. And now I will say that, okay, you randomly pick one object out of this box. Let's suppose you have picked square. Now I'm not putting it back in this particular box. Okay. Now what is the probability of picking this square at the first time? It is 3 by 5, right? Say yes or no. 3 by 5.
Yes.
Yes. Now, once you have picked it up, what is the probability that again you will pick the square item? What will be the probability?
2 by 4.
2 by 4. You got it. Okay. So now let's suppose in this particular use case, these square boxes are nothing but known as illegal computers. Okay. Now here, if one first computer, if I picked it up as illegal, then the probability of other computer to be picked up as illegal would be dependent on this, right? On the first pick, it will be different, right? So that's what it is showing as a dependent events. So if there is a situation like this where the events uh, are dependent on each other, there we will go with a hypergeometric distribution. So the binomial distribution is applicable when selecting from a finite population with replacement. There, every item will have a same probability. Every customer, whether he will buy, make a purchase or not, it's the same probability. But here in this case, it's different. So wherever it is different, where the probability of an item to be picked up is dependent on the first item, what has been picked. Now that kind of sampling is known as without replacement. Okay, so if it is picked, then it is gone from this particular box. It is not existing now. Okay, now the probability of picking up other item would be different. Okay, the probability would be different. So now if we have this kind of scenario, there we will go with a hypergeometric distribution.
So,
Okay.
so we cannot use this for infinite population.
No, we cannot use it for entire population.
Okay.
Yeah. So see here, that's the reason this is important. We need to have a population size. It cannot be infinite. Here we need to have a sample size. Here we need to have a number of successes in population, and the X is the number of successes in sample. Now this is the formula. You need not to by heart this formula. It is just for your reference. In Python, you just need to call the right function for each of the distribution and pass the parameters, and it will give you the probability. Okay, so no need of by hearting or remembering these formulas. It is n minus a combination of n minus x divided by capital N combination of small n. Now this is the formula. Okay, now you have to substitute the values to this and you will able to get the answer. So for example, in this particular problem, here what is the population size? N is 10. I'm saying different computers are checked from 10 in the department. So in the department, there are 10. So this is my population size. And 4 of the 10 computers have illegal software loaded. Okay, so this is A. A is the number of successes in the population. Now this is for sample. Now I want to find out, I want to draw a sample out of this particular population. And while drawing that population sample, I need to find out what is the chance that 2 out of the 3 selected computers may have a illegal software loaded. This is a very small example I'm telling you. So here the sample size is 3 and the number of successes in the sample I'm interested for is x is equal to 2. Now I'll go and substitute that into this particular formula, and now the probability of getting x equal to 2 is equal to 0.3. So the probability that 2 of the 3 selected computers have illegal software loaded is 30%. Okay. So here, this is very much similar to binomial distribution, but you have to keep it very clear in mind that, okay, what you're dealing with, okay, whether it is a finite or infinite population. If it is finite, then you have to go with hypergeometric. At the same time, it has to be a sample without replacement, which you are referring to. Okay, so there you have to go with a hypergeometric. So like that, you have several distributions, guys. Okay, so you have hypergeometric. This is hypergeometry. Then you have log normal distribution. Then you have Weibull distribution. There are several distributions. Okay, so if you go deep into statistics, then you will understand each of those distributions and also the scenarios where those distributions can be used. So if you encounter any such scenario, then you can quickly use these kind of distributions and you can solve that particular problem. In Python, it is relatively easier. If you know the distribution, you just call that particular distribution with a function and pass those parameters. You can quickly able to calculate the probabilities. Okay, so shall we continue? Is that okay? Or shall we stop? So I have another 3 distributions. If it is okay, then I'll cover these 3 distributions today, and then tomorrow we can get into Python. Okay. Is that okay for all?
Yes.
Okay. Fine. Good. So now we're talking about the continuous distribution. So continuous, so where all these random variable x so far we discussed, those were capturing only the values which are discrete, like in the binomial distribution, like 0, 1, 2, 3. Like then we discussed about Poisson. There also the rate of occurrence was countable numbers. Okay, it was not into decimals. So there also, it is more of a discrete number. Then we talked about hypergeometric. Here also, those are like countable numbers. Now, when we are talking about a random variable where it can take any continuous or any decimal values, there we go ahead with the continuous variable distribution. Okay, so for example, if you are measuring a thickness of an item, thickness of item can take any value in any decimal numbers. Okay, time required to complete a task, temperature of a particular solution, or height, all these are numerical values which can be measured in any decimal places. So now if you have these kind of data, then you have to refer to these kind of distributions. So special distributions in continuous distribution families: uniform, normal, and exponential. Okay, let's talk about uniform distribution. It's very simple. Uniform distribution, by name itself, you can understand every value in this particular distribution will have a equal probability. Okay. So the uniform distribution is a probability distribution that has equal probabilities for all the possible outcomes of that random variable. And that the shape of this distribution will be in the form of rectangle. Because see here, this is X, this is PDF, probability density function. So now every value will have a equal probability. Okay, like this. So let's suppose I want to find out, and now you have to define this uniform distribution is between what range. Okay, so it cannot be minus infinity to plus infinity. Okay, it has to be a certain range, and in that range, let's suppose you want to find out the probability of a particular value. And if you know that if it's a uniform distribution, the probability can be calculated simply by this particular formula. Okay, it is 1 divided by the range. That's all. Okay, and that's the probability which you can assign to every value between this particular range. Okay, so if X is your random variable and you want to find out the probability of any value between this particular range will be equal to 1 minus b minus a, which is nothing but the range. For any other values apart from the values within this range will have a probability equal to 0. Okay, and the entire area under this curve would be equal to 1. Just like in normal distribution, if you remember, that was also for continuous, the entire probability within this particular curve will be equal to 1. So now this is uniform, this is normal. Okay, in this normal distribution, you have seen that the probability of getting any number will have a different probabilities based on this distribution. While in this uniform distribution, every value within this particular range will have a equal probability. Now, where we use this, okay, generally, let's suppose, I have one particular variable where I do not want to be biased in terms of selecting the values. Okay. For example, age of the customer. Okay. I don't want to be biased saying that, okay, these kind of age group or aged people, okay, generally come into my store more often, okay, or more often. So there I can go with a uniform distribution. And while I'm generating the data about the customer's age, I'll be completely unbiased in terms of selecting the age between a particular range. Okay, there I will go with a uniform distribution. So for example, this example, consider the random variable X representing the flight time of an airplane traveling from Delhi to Mumbai. Now, flight time is a continuous variable. It can take values in decimals, right? Suppose the flight time can be any value in the interval between 120 to 140 minutes. Okay, that's generally the flight time of this airplane traveling from Delhi to Mumbai. Because the random variable X can assume any value in that particular interval. So now this X, which is random variable, it can take any value between 120 to 140 minutes. Now I am very much interested about any one particular value. For example, I want to find out what is the probability that this flight would take around 130 minutes, probability of 130 minutes. So here it is nothing but 1 by 140 minus 120, which is equal to 1 by 20. That would be the probability. Okay. So here it is. So any value between this particular range will have a equal probability as 1 by 20. Okay, if I'm considering this particular random variable will follow a uniform probability distribution, then only I will consider it as same. Okay, if I consider it as a uniform distribution, there the probability may change. Okay, for X equal to 130. Okay, if I want to find out what is the probability of the flight time will take somewhere between 120 to 130. So now I will calculate this particular range which I'm interested at, and that I will multiply with the probability 1 by 20. So it would be 10 by 20. So it's just 0.5%, 50%. So this is how you can calculate the probability of a particular range also. Okay. So for example, now you tell me what is the probability that X would be somewhere between 125 to 132. Anybody?
7 into 1 by 1 by 20.
Yeah, 7 into 1 by 20. 7 by 1 by 20. Yeah, this would be the answer. Okay, that's how, by using this uniform distribution, you can calculate the probabilities of these values. Now coming to exponential probability distribution. So now this exponential probability distribution is almost like opposite to the Poisson distribution. In the Poisson distribution, we are fixing the time and then we are finding out the probability of the events to occur. Now here, in this exponential probability distribution, here we are measuring the time between the two events. Okay. For example, time between the vehicle's arrival at a toll booth. Okay. So in the you have seen, right, in multiple tolls. Okay. How many counters need to be there. Okay, it depends on the vehicle arrivals. If the time between the two vehicles is uh, is is large enough, okay, then you don't require so many toll booths. Okay, if it is very small, like in per minute, you are getting between the two cars, the time is very short. For example, it is just few seconds. Then you require more toll booths. So now this is a different scenario than Poisson. Here we are calculating the time and between the two events to occur, between the two events occurring, and based on that time, we can make the decisions. Now this time will be continuous. It can take any decimal value. Okay. For example, time required to complete a questionnaire, distance between major defects in a highway. Okay. So here between the two events, whatever we are measuring, that we will consider that it will follow a exponential probability distribution. The formula of this density function is 1 by mu into e raised to power minus x by mu. Mu is nothing but the mean, which you need to know, and this x is nothing but the value which you are interested for. Okay. So now I'll take a example here. Suppose that x represents the loading time for a truck at a loading dock. Okay, and follows this exponential distribution. If the mean or the average loading time is 15 minutes, 15 minutes for loading a particular truck is, let's suppose, 15 minutes. Mu is given. The appropriate probability density function for x is given by like this. Okay. Now, if you want to find out what is the probability of loading time as 12 minutes, then you just put x equal to 12 and it will give you the probability of x equal to 12. Okay, so now this distribution looks like this. Exponential, right? Exponential would be like this, or exponential would be like this. Okay. So whenever we say that it's exponentially, it is increasing or exponentially it is decreasing. So it typically you will find the curve like this. If I say probability of x less than equal to 6, then I'm talking about this particular region. Okay. If I'm saying probability of x between x6 and 18, then what you have to do is first you have to find out the probability of x less than 18 and then subtract the probability of x less than 6, just like the way we have done the normal distribution. So out of this, the entire portion, you have to subtract this particular area. Then you will get this part. Okay. Let's do this. Okay. The time between arrivals of the cars at a petrol pump follows a exponential probability distribution with a mean time between arrival is 3 minutes. Okay, so here the mu is equal to 3 minutes. The petrol pump owner would like to know the probability that the time between the two successive arrivals will be 2 minutes or less. Okay. The mean, you know that typically it takes 3 minutes between the two cars, okay, in a petrol pump. But he is interested to know that what is the chance that I may get two cars in 2 minutes or less than 2 minutes, okay, in the petrol pump. If it is higher probability, if it is significantly higher, then I will go and manage my pump accordingly. I'll put more resources or more tanks, okay. Or if it is less, then I'll go ahead the way it is, okay. So here I'm interested with probability of x less than equal to 2. So I'll use this particular formula, okay, which is this. E is nothing but your 2.17. Okay, 2.71. So this is 1 minus 2.71 raised to the power minus 2 by 3. 3 is your mu. Okay, so which will give me as, sorry, it is 0.4866. So with this probability density function, I can able to calculate the probability of x less than equal to 2. Is this clear, guys? Now, relationship between Poisson and exponential is the Poisson distribution provides an appropriate description of the number of occurrence per interval, where the exponential distribution provides an appropriate description of the length of the interval between the occurrence. So that's the relationship between the Poisson and exponential. And when you are identifying any kind of scenario, you have to make sure, like, which scenario you are dealing with, whether it is related to the Poisson or whether it is related to exponential. Accordingly, you have to choose the right method and to calculate the probabilities.
In the exponential,
Yeah,
the petrol pump problem, what
yeah,
was that was the interval, 2 minutes or less.
2 minutes or less.
So
So
here
this would be
0.48 represents the minutes.
sorry,
0.48 represents the minutes or the
this is the
interval.
probability. It's a
Okay.
percentage. It's a 49% chance that okay, you will get
Minutes or less.
two cars within 2 minutes or 2 or less than 2 minutes. So which is pretty high, okay, which is 49% chance. So if it is a 49% chance, then business has to take a decision, right? Okay, whether it is possible to fulfill that much demand, okay, in the petrol pump or not.
In
Got
the
it?
same scenario, can we get like a rate as well? Like uh
Rate means
for the Poisson distribution if I want to apply. So what would be my
yeah.
another scenario in the same petrol pump example?
Okay, so you're saying with this can we calculate the rate, right? That's what you're saying.
Yeah.
See here, see for example, you have the uh, number of arrivals is 10 cars per hour. Okay, the average time between the car arriving would be this 0.1 hour per car. So with this method, you can convert. So now if you want to find out this particular thing, so for example, 1 second, 2 minutes. 2 minutes means 2 by 60. So you're saying 2 by 60 hour per car. Okay, so every car, between every two cars, I'm saying it takes 2 minutes, right? So it is 2 by 60 hour per car. Okay. To calculate that a rate, now it would be 1 by 60, 2 by 60. 1 by 60, 2 by 60. So it would be 60. It would be 0.5. 0.5 cars per hour. So this is how you have to calculate. If I'm just check it, okay, if I've done it correctly or not. So this is how you can convert into the rate. But see, why do we need it? Okay, so here what we are trying to understand is, I want to know that, okay, how much time it may take, for other car to come to my petrol pump. When one car I'm already filling, so if the second, in how much time I may expect the another car, whether that arrival will be in 2 minutes or less than 2 minutes. That's something I want to calculate. So for that, I will go with this exponential probability distribution. And based on that, I just calculated, I found that, okay, there is a 49% chance that, okay, I may get, within 2 minutes, I may get another car for fuel. Now, can I able to fulfill that or not? That I have to decide. If with one station, if I cannot fulfill, then I have to add one more fuel station. Okay.
Okay. Got it.
Okay. This normal distribution we have already spoken, so I will not spend a lot of time. Okay, so this normal distribution may take any value between minus infinity to plus infinity. Okay, now this has a very unique property that it requires mean and the sigma. Okay, these are the two important parameters which we need to know, to define what distribution it is. Okay, if it is mu is equal to 0 and standard deviation is equal to 1, then this normal distribution, we can call it as a standard normal distribution. Now, this has a very complex, complicated formula. But if you look closely this particular formula, you will understand that. Do you know what is this formula? The Z score formula is x minus mu by sigma. Okay, that is this. You can also put it as 1 by 2 Z square. Okay, now, okay. Now, for example, you are assuming any particular data following a normal distribution and you want to find out the probability of a particular number, okay, particular value, okay, on that particular distribution. And if you know the mean, the mu and the standard deviation of this particular distribution, you just substitute the values and just take whatever value of x you want to find out the probability, just substitute that value here and you can able to calculate the probability, okay, of that particular value or less than that particular value through this method. So generally we use Z distribution if we know that this distribution is following a having a mu is equal to 0 and standard deviation equal to 1, then we go with the Z distribution directly. If we do not know, then we go with this particular formula and we substitute whatever mu we have, for that particular data and the standard deviation of that particular data, and we substitute that into this particular formula to calculate the probability of density function of that particular value. Okay, so here E means it's a natural logarithm constant 2.71, pi is 3.14, mu is the mean, and sigma is the standard deviation. Okay. Now this is my normal distribution. So that's all, guys. So these are the distributions. So if you are aware of which distribution to use in which kind of scenario, then you can directly use this distribution to calculate the probabilities. And even if you have some idea about these variables, then you can use the parameters of these distributions to generate the data for that particular variable. So in both the scenarios, this distribution plays a vital role in terms of calculating the probabilities or even generating the data. Okay, so now tomorrow we'll see that, how we can calculate the probabilities, how we can generate the data, by using Python, by using appropriate distribution. Okay, and we'll take different scenarios, we'll take multiple use cases, and then we will solve it by using Python. So I'll take a pause here. Let me know anybody has any question. Okay. All right. Thank you guys, and we'll connect tomorrow. Take care.
Thank you.
Bye.